All right, testing, testing. All right, good there. All right, quick check if anybody can anybody hear me before I get started here. Waiting for someone to jump on. Let me know if you can. Let me know if you can hear me. I'm still getting things set up here. Open. And there we go. All right, so I got two of y'all on here watching. If you can hear me, please let me know. Just making sure audio is streaming. And everything looks good. Microphone, system sound output. Yeah. All right. All right, great. Hey, appreciate it. All right, so we had a person on YouTube that chimed in and pointed out this really cool, like a really cool cooling unit, right? So I really like the fact that, you know, when I stream designs, nobody ever does this because everyone's got this damn pride and ego about them where, you know, they're very concerned about a design getting stolen. I guess I'm not, because the people we have to worry about designing, or, you know, stealing our designs today, they're the Chinese. You know, the Chinese they'll just take your design, copy it, and what are you gonna do? Sue China? Go to war with them? You know, you're not gonna do anything. They have a fake Walt Disney World over there. Walt Disney's been trying to sue them for a long time. You know, they're selling Disney World DVDs and things like that, and you know, what are you gonna do? You have to go to war. That's what you gotta do. I mean, you're not gonna take them to the courtroom and get money out of them. I mean, they just don't care. They have, like, the Chinese kind of have a bit of a sour taste toward America in general, especially with us threatening to, you know, not prevent them from invading Taiwan, which they claim as their territory. So, anyways, I don't care. I'll show the designs, because this is a conceptual design, so I'm not going to be spending too much time here. I just want to give it an update, and you know, some of y'all watching chimed in. Toolman on YouTube, excuse me, shared this, and I was like, man, I wish I would have found that like earlier. I would have bought it. It's $300 though. That's the only problem. It's $291 for this, and I'm, you know, I'm trying to think, like, man, I could put my diodes in between each one of those copper tubes that are in there. But at the same time, I'm also kind of cheap, right? Like, I'm looking at this, I'm like, I gotta make this shit. I'll just slap a block of aluminum down on my CNC machine, and I'll mill all that crap out. Take a blowtorch and heat that copper up. Stick it on my anvil. Hit it with a hammer it flat into place. Bada bing, bada boom, baby. I would make my own. You know, and I have Hardy tools to round off the copper right here. I could completely manufacture and replicate this. So I don't know if, you know, if I bought it for $291, it's because I'm being lazy. That would be the only reason I'd spend that kind of money. But regardless, you know, he pointed these out for intercooling systems, and I'm like, hey, that's pretty cool, because now we're also cooling the plate on top of, you know, putting water on it, and you know, if I put the water cooler on top of that, and we've pumped from out of this plate into the water tank reservoir, out of the water tank reservoir through the, you know, let's see here, let's hide this guy out, get this out of the way, and we'll hide the lens here. So imagine this plate in blue right here. Imagine it was this guy right here. It's this. Then we would have to put the diodes in between. Yeah, cookie. You'd have to put the diode holes in between there. That way you can mount the diodes and not puncture the copper tubing. and it would be pretty much straight up drawing the heat to a very maximized level. But that's also, you know, that would, because of the thickness of that aluminum, we're adding a lot of weight. So I'm trying to keep, I mean, we're already adding weight from water volume. But still, the point here is that I wouldn't even have this as an option if it wasn't for the fact that I didn't live stream my design and, you know, do it, you know, also fearlessly. Because I'm not dynamic. I have ADHD. I like, you know, I can build this and design it, and after I built like 3 of them, I can't do it no more. I have to pay somebody to build them, because then I hate it. I'm like, you know, I already made it. Like the high that I got from designing it and watching it come together, that's already over with. I've done it, achieved it. So for now, I've got parts here. So here's what I'm doing today. Here's what's going on. I didn't design this component in, and this is again what we're seeing here on the screen. This is kind of like your rough draft. I kind of haphazardly did this on the software side, so I have to redesign this entire thing. Like everything about this is not, you know, look at the holes. See, they're kind of like not perfect. That's because I wasn't making a realistic design. I was just trying to get together and think in my head, like rough drafting it, like how would I fit all this shit together and, you know, make it work? How am I going to fit this water tank in there? So right now, like here's a bulkhead, an all metal high heat bulkhead. And this would go into the green tank, or to the tank highlighted in blue. And right now, if I measure this guy, it's 50 millimeters length. Let's see, if we cut, hold on, if I were to tighten that down to the halfway mark, and ballpark it at 25 millimeter. And here are they in metric. I still can't stand using, you know, inches. You know, that's 971 thousandths. I guess I'm so used to metric, it just makes sense. You know, it's just basic numbers. One point this, 1 point that, all base 10, you know. I like that versus dealing with a bunch of fractions. Maybe I'll convert to our American standard one day. Okay, so 25 millimeter. Would my tank have fit? Let me redo that. Okay, 47.728 millimeters distance. So this is about 50 millimeters in height. It definitely would fit this. So that means that I can reduce this down. This is kind of too high up. I don't want to keep it so high up. And for those of you who are curious, watch my previous video. I'm going to take aluminum rods and I'm going to braze the gap right here on the inside of that and the outside. So I'm going to use, technically it's soldering. I'm going to solder / braze it with real high heat with like a MAP gas, you know, aka blowtorch. Heat this up and then run solder along there. I watch a lot of videos of people aluminum welding compressors and things that have to hold pressure and water, and I was pretty impressed. And I was going to TIG weld all this, but after watching that, I didn't have to do that. I didn't have to go that direction. So anyhow, what I'm going to be doing in this particular live stream here is, now I want to smoke some pot. I got to design all these little components. So I'm only going to do like 3. I'm going to design this, the power switch. This is a 25 amp power switch. And then here's the hot water pump. For the hot water, it's going to have to pump. So I need to design this guy. Yeah. And part of me's thinking, like, I don't know, like in my design, so here's why conceptual is not, well, why it's conceptual. here is my makeshift little pump. You know, I didn't dimension it. I just kind of put it on there, and all that fun jazz. But this presents a little bit of a problem. What is that problem? Well, it's going to get hot as flagnog. I mean, it's going to be right here. It's going to be cooking, man. That damn grow light plate's going to get hot as shit. So I think what I'll do is we need to get this guy. We're gonna need to get this pump. You know, it's already gonna be pumping hot water. The last thing I want it to do is be getting superheated from the grow light plate, and it cause it to fail or deprecate its lifespan. So, depreciate. Yeah. Not the usual contextual. Scroll on down there, computer. All right. So I think what we'll do here is I'll flange that out. That's what we'll do. So again, this is still conceptual, but I have to completely redesign this grow light. But just to share with you, I think a solution to what I could do here is, and then let you visualize it along with me as I'm doing this. Okay, let's see here. Body. Okay. Okay, so I'm going to go ahead and flange that out. And, angle. You know, there's a way I can do. No, it's not it. Let me cancel that there. And I'm just going to kind of, again, going to ballpark it. See, in the actual design, that may not be perfectly centered. See, like, this, the end of that may be, you know, further away from the center. Yeah, so you can kind of see right there. See how it's kind of like lopsided? So let me go ahead and keep, my OCD's kicking in. Let me at least keep it somewhat semi-honest to the concentricity of the design. We'll come up this way. Bam. And let me hide that guy. I want to cut you in half. Darn it. Well, why did I do that for? I want to cut a hole in that tube. Don't want to cut a hole. Where's our freaking tubes at? Radiator, pump. No, that's not it. Let me do something real quick. Cancel here. Let me hide that. Mo better. That Mo better. Then we kind of need like a little bracket to mount it. Well, what did I do there? No. It's complaining. Let me bring it up a notch. There. And I'll go ahead and correct it here in a second. What did I have? 57.5. There, no. Go 58. Yeah, there, well, no, that's too much. A little too much. 57.8. Hmm. .7. Yeah, looks good. Good enough. Okay. Let's just make this thing green, just so we can see it better. Go. Nah, you know what? That's ugly. I don't like it. Let me just go ahead and go back here. Edit that. And then we'll dimensionalize it. So from there, darn it, from there to there, do 45. And U to U, yeah, stays 45. Dimensionally driven sketch. That lines it up a little bit. All right. You disappear, and we're gonna move that water pump. I don't know if y'all can hear the music, man, but I'm all be bopping, man. See, something like that will it'll keep that water pump off of the freaking off the design, and then just put some screw holes here in there. Here in a second, I'll do a 3D render, and we can see what it'll look like in a more realistic render. Let me get my big old freaking camera view out of the way so you can see some stuff. Yeah, where's all component 1, component 2. Okay, there. There. All right. Whoa. What happened there? Something kind of got jacked up. Oh, I know what happened. Yeah. That's not supposed to be there. And I've got a tube that I'm not able to find right now. So that's actually why I have to redesign this, because I was kind of like haphazardly putting this thing together. So there's the one. Okay, that's the one I'm looking for. All right. And now let me jump in here and let me show you the headache of running tubes and stuff in a 3D environment. It's really like, it's really a pain in the ass. Check this shit out. Actually, I'm gonna have to just completely all out delete those. Never mind. Let me rebuild these. Let me rebuild them. Here, you'll get a first-hand view of why you don't see me running the wires in the designs. I do when I'm at the final stages of the design, because it annoys me not to see like everything that's supposed to be in the final product. Just going to delete it, and we are going to redo it. All right. So, project this bad boy. Okay. I'm going to throw a 1, 2, 3. Check. Now we're going to do include three-dimensional geometry. Three-dimensional geometry. Check this shit out. This is pretty awesome. This is why wires are a pain in the ass to design. I make it look easy, but try it. Try it sometime. What happens is like things want to get squirrely, where it just looks all weird. Like, let's see, you might get a glimpse of it right now. I'm kind of flowing pretty good here. Okay, let me project to this guy here. No, that's not what I want to do. What happened there? So it keeps throwing this damn circle up the top. Shit is driving me nuts. Projection link. I might have to go from the pump to the. Yeah, I know what I'm gonna do. I know what to do right here. Like I said, wires are like a pain in the ass. Or tubes, or whatever the case is. 1, 2, 3. All right, you might get to see what I'm talking about. Now include 3D geometry. Right there. Yeah. All right. Boom. So check this. See how it looked all. Here's the nightmare with it. See how it looked all good from one angle? Like, it looks all good over here, and then boom, it's shooting off into 3D space, man. Not too bad, though. Still semi-okay. Alright, we're going to connect the dots and do some kung fu with a coincident relationship. And we're going to do another coincident relationship over here, which we already have one by default. And we are going to throw some spline into there. Start a spline point. Oh, what happened? It went funky. Okay, here we go. We're back in action. I'm going to throw one there, throw one there. Come from this view here. I need it to look realistic. Okay. Wow. It's looking all funky and weird right there. Let's raise this one up. Maybe like that. Yeah. That looked no better. Alright, now we're going to do a sweep from this profile. Oh, you did not. Oh, and that's a revolve. I was like, what the hell's going on here? Sweep to this path. We're going to do new component. Click OK. Make that shit clear, man. Boom. Now we have tubes and shit. It's going good. Alright. We got uno más. Uno más, and then we'll start rendering things. I gotta put some, like, you know why ADHD works with this shit really good? Because I'm like seeing everything wrong, and instead of like finishing the other tube, I'm like, well, hold on there. I need to put these holes over here so I don't forget later, because if I don't do it now, I'm going to forget later, and it's not going to get done. Mirror that to... It's funny, all this is almost being done for nothing, because this is not the actual design. And that's where, so technically, if I wasn't being compulsive, like, oh, I got to make sure it's my concept is going to be almost as accurate as an actual design, I wouldn't have to put those holes right there. I'd just leave it alone, and I would mentally know that when I remake this whole thing, I will put the holes in there. And yes, I could, for those of you who are that CAD people, I could completely go back through and make all these holes perfect and use this exact design to make this exact design and just correct everything and take it from a rough draft to final draft it. But there's a reason why. Every time I make, for anyone that may be a CAD person, every time I work on a component of the assembly, I do not activate the component while I am working on the project. So all of the work that's being done is subcomponentized in the parent hierarchy of the entire design tree over here of all my component modules. So every time I make a change, I have to either it's a global change or it's a localized change native to that component in the tree. So I've been kind of globalizing everything, and that is bad practice. So that's why I will redo it, completely rebuild it. And also because when you do that, when you completely go from your rough draft and you redesign it, your brain thinks differently. You tend to make a more beautiful piece of art, you know. All right, let's go back here. I'm gonna project to there. Bit point spline, boom, boom, bang, done. All right. So right now we're in a 2D plane, which means that that line isn't going to want to go up or down, left or right. And to do that, we need to include our 3D geometry. And we'll do that right there. Regular spline. Done. That and that be coincident. There we go. What a coincidence. It's a coincidence. Try saying coincidence when you have a lisp problem. You know how many years when I was a little kid, all I heard in school was suffering succotash. But so it's okay. It's kind of a form of autism. A lot of people have accelerated mindsets where their brain is running so fast, the words seem to be post-processing, and it kind of leads to you get yourself in trouble sometimes. You end up saying things before you think about what you're saying, and you're like, oh, I shouldn't have said that. Maybe I should have. You know, like you have to train yourself. It's like people with speech issues, different kind of speech impediments, or people with, I mean, short of having Tourette syndrome, you have to learn how to keep your mouth shut. Bam. Go front face right here. Bam again. All right. All right, let's see what she looks like when we turn it into the real deal. So I think right here, this placement where we're hovering above the heater, the main heater reservoir, the water reservoir here. We're basically not touching anything hot, you know, like, and I could just to kind of like, if I really want to be anal retentive about thermodynamics, I could just go ahead and chop a couple holes right here. Come on, computer. And do something kind of like that, you know. And this would keep any of the heat built up from the radiators that are actively having hot water circulated through them and conducting heat into this lift frame here. Basically, this piece of metal right here is holding all the active, passive, cooled water radiators, and by cutting these little slits out right here, it's hard to say when you have a lisp problem. Little slit mouth liquor, slits mouth liquor. Whenever you have these little cuts right here, it doesn't have enough surface area to fully conduct heat and translocate that heat over to this water pump. So it's kind of like a minor detail with essential reasoning behind it, practicality. All right, let's bring back all the missing stuff. And then I've got to actually designing the components because I want to build this thing, have all the parts to build this thing. And yeah, I have everything to build it. I'll be getting the metal cut probably next week. So, all right, so main chassis, main board is there. I mean, bulkhead. Let me name those hose. 1, hose 2. Alright, not top chassis. And that's the other thing when I'm conceptually designing it. I get a bad habit of not naming everything. Host 4 or host 3, host 4, and we got rounding 1. No, I'm gonna hide that. I'll wait to keep that out. Chassis right here. Okay. We'll bring that back. We're kind of missing our lens right now. And I could run wires here. Wires go from each diode, just in case you're curious. Later I'll CAD design them in. Just I'm not going to do it on the concept design because it's an extensive amount of work running wires. As you can see, running those tubes takes a fair amount of time. And I'd be weaving those wires three-dimensionally through each one of these holes from this red to that red to that red in a parallel connection, and then all the wires get fed through here, through that loop, through the back here, and connected to our power cord plug right there. Bam. There's the electric. That is the connection. I am missing the lens. Okay, let me bring the lens back, and then we'll do a 3D render. And then I've got to, alright, so now we have our lens. Check it out. Okay. Do a realistic render. Like I'm rendering with an RTX 4090. It's a really fast graphics card, the fastest one they make. Okay, there's a render. It's a pretty much full render there. So render means like it's a realistic rendition of what the design is supposed to look like when I really make it. Cool there, man. So, every glass some dials, simulation, photons, light, and reflected on. It gets pretty CPU or even graphically intensive. Like I have a color graphics card and a 16 core or 16 core processor. Okay, there we go. She is rendered out. So pretty neat. Now let's put it all together and then concept design. Let's finish with the main parts back on. Top chassis. Put our hair comes back on. And we ventilate. Well, what's all that water heating action you gotta do if we don't get rid of the damn heat? So one thing I like to emphasize to anybody, emphasize after a render, is after I build this room, despite its problem, the very paradigm of heating and cooling. This design really can't get any better than fan cooling and water cooled radiator system that is also being actively ventilated out of the EcoSmall heating and actively ventilated. Without actively ventilating all of this heat out, I'm going to tell you something that just makes you stare at, like stare at a deer staring at. Let's try to kill a render here. And I'm going to have to bring up another design to show you something. Real quick, before I get started here. To the 0.5 gigawatt. So here is a 0.5 gigawatt design. A lot of y'all are growing with this grow light, and so here's my question. You know, for those that have been following me for a while, you probably know the answer to this question. But for those that haven't, let's present this question of thermodynamics. All right, so right here we have a 16 diode 0.5 gigawatt. Okay, so 16 times 50 watts. Each diode. Each one of these diodes is 50 watts. So what is that? 800 watts. So if you have 800 watts here on this plate, this grow light is 800 watts, for example. And there is no fans. There is no water cooling. There's no cooling whatsoever. The only cooling being done is this plate is taking heat away from these diodes. So if we stuck this grow light in a tent and we sealed the tent up, and we also stuck this super cool, awesome, epic looking water cooled design, okay, that has all these radiators and fans. Let's say, just for this example, for the sake of science and to quiz you, this design also had 16 diodes. It had the same amount of diodes as this 0.5 gigawatt. If I stuck this 0.5 gigawatt in a completely sealed grow tent, a 4x4 grow tent, and I stuck this water-cooled grow light also in another 4x4 grow tent, and we completely sealed up both of those grow tents, and we turned those grow lights on and we left them on for 8 hours. Both grow tents are in the same room, same temperature in the room, except each one of these grow lights are concealed inside of a 4x4 grow tent that's completely sealed off so no air can flow in and have any effect to the temperature. Which grow tent is going to be cooler after 8 hours? If we were to open the grow tent, or we had a temperature sensor being data logging the temperature in there, after 8 hours, which grow tent would be the hottest? Would it be the one with the water cooled unit, or would it be the one that has the flat plate design? Well, the answer there is that they're both going to be the same heat. You know, and it doesn't matter the technology. This whole grow light right here, it could be HLG 550's quantum board. If it's 800 watts, and this grow light, which is also 800 watts, are both in a grow tent, they're both going to get the same height, even though this one's water cooled and the other ones are not water cooled. Because watts is watts. Watts is heat. So 1 watt equals 3.41 BTUs of heat. So it behooves people, and they're like, oh, this grow light, you know, your grow light, it doesn't have no fans or anything, like when referring to the plate design, which, mind you, is probably the toughest grow light design on the planet because it's all metal. The thing in there is 800 watts is still 800 watts times 3.41 BTUs of heat, roughly 2,500 BTUs of heat. So it doesn't matter if I build you a cool-ass grow light, and no matter what technology you pick, if this was an HPS bulb, say this LED right here is 1,000 true watt straw, and you have 1,000 true watt straw HPS bulb, and you put them both in a different grow tent, even though this one is water cooled and the HPS is obviously not water cooled, and you put them in a grow tent and you seal the grow tent up, after 8 hours of being left on, both grow tents are going to be the same temperature, because a watt is 3.41 BTUs of heat production. So if you're in question of that, you can go ahead and Google that yourself. 1 watt equals 3.14 or 3.41 BTUs of heat. The only way to cancel out heat is with, or BTUs of heat is with BTUs of AC or cold. So that's why you have heaters that are rated in BTUs of heat and air conditioners that are rated in BTUs of cold. It takes 1 BTU of cold to eliminate 1 BTU of heat, or interchangeably, it takes 1 BTU of heat to cancel 1 BTU of cold. And since it's wintertime, you're trying to heat your house up. So the trick of the trade and the cheat and hack of getting rid of heat that this grow light is producing isn't cool fans and water cooling and heat sinks and all that. What does a heat sink do? This water cooled system is basically a heat sink on crack. What does a heat sink do? All a heat sink does is it moves heat away from the diode. That's all it does. It displaces the heat, moves it to a different location, because heat molecularly is attracted to cold. And so a heat sink will draw the heat away from the diode, eliminating a high heat environment for that diode, extending the metallurgic properties of the diode so that the diode lasts longer and has a longer lifespan. But it doesn't, essentially, it does not remove the very nature that a grow light, without ventilating the heat that grow light produces out of your building, a grow light's essentially a freaking bona fide, glorified heater. That's all it is. And it's going to be a real problem. And today, everyone's jumped on the LED bandwagon, and you have all these LEDs are real wide, very widespread, 500, 600, 800,000 watts. And you're producing tons of BTUs of heat at your commercial grow environment. And the problem with that is that now you need $100,000 HVAC to counter your 100, 200 grow lights in your grow operation. So how do you solve that problem of that equation? You do it right here, my friend. So whether we water cool the grow light or we just trap the heat up, which I'll show you the next genesis to this design. And I'm actually building this. Let me move my face out of the way here. The next genesis to the 0.5 gigawatt design, the plate design that you've seen, is the ventilated gigawatt. Now I already built one of them. I built this guy right here. Many of you that watch my channel, you have watched me build this one. You're like, oh, that's big and heavy. No, it's not. It's really not, because there's no drivers. Look at your HLG 680 volt or 680 watt mean well driver. It's like a freaking 20-pound brick. I mean, it's heavy and it's hot. You cook a damn egg on top of your mean well driver. I could show you how much weight this freaking driver is right here. Check it out. Because it's in steel. Let's see if I can pull up properties here. It's 160.313 ounces. Okay, we all, as growers, we all know, how many ounces are in a pound, right? So let's see here. 1, 6. It's a 10-pound freaking. Just this chassis right here is 10 pounds. 10 pounds. That's lighter than your mean well driver. It's way lighter. Because these chips are driverless. They're converting AC to DC with microinversion technology. So you're not really needing to pack all that, inverter weight on your design here. Probably the heaviest thing on this design would be the aluminum sheet here. And I already know off the top of my head from shipping these out that by itself is 12 pounds. So that's why I got rid of this plate and we moved over to this design. This design is entirely all sheet metal. And it will roughly weigh about, let's see, 124. So 7.75 pounds for the top side. So it's a two-part system. It's a kind of like, think of like a pizza box. We have a box that's inside of a box, right? So 7 pounds plus 124. 14 pounds total in metal. I would say here we'll measure that out. Ventilation 1, vent 1. .6 ounces, so half a pound. So we're at 14.5 pounds. And those are in aluminum. Let's see here. Aluminum. Let me type in the word aluminum. Okay. Physical material. Change to metal, aluminum. All right, let's see your properties. No, still reading it. Steel. Appearance is aluminum. How did I change the freaking physical properties? Yeah, there we go. It should be this. Okay. There we go. Okay, so each one of the diode caps in cast aluminum has a mass of 1.19 ounces. We have 24 diodes times 1.19, 28.77 divided by 16, 1.7 pounds. We're looking at a total system weight of we'll just ballpark it at 17 pounds. That's still lighter than like most of your mean well 680 drivers, and we're driving a 2,000 watt system and we're ventilating it. Talk about lightweight. We're talking that go grab a 15-pound dumbbell in your hands. That's how much this entire grow light weighs. Now, for those mean well snobs out there, yes, when you're micro inverting, you're not going to have as high of an efficient driver as a mean well driver. But these things still pump out 100 volts VDC, and they're still insanely bright with ultra high PPFD because they're still running LM301H Evo technology. So regardless of the driver efficiency, they're still putting out the freaking PPFD. All right, anyhow, enough on that. I've got to get back to component design here, or I'm going to be behind on schedule. Then I got to jump off here and start doing some Android application programming within Android Studio, programming in Java. I thought some of you might find that fascinating. It's so funny how many times I ask somebody, if a 800 watt grow light that has fans and a water cooled system versus a 800 watt grow light that has no fans or heat sinks whatsoever, which one's going to make your grow tent hotter? And some of them think it's a trick question, like, oh, well, maybe the one that doesn't have the water cooling and fans and heat sinks, maybe that one's a cooler one. They self-sabotage their own thinking, because most people would think that the bait and trap to that whole question is, well, the water-cooled one should be the cooler running one, but ultimately it doesn't matter regardless of the system. Both of them still follow the laws of thermodynamics, where 1 watt equals 3.41 BTUs of heat. All right, let's jump on over to this folder right here, and I'm going to start designing this. I got to design this part right here. So this is a bulkhead. This is where we're going to connect our tubing to the water-cooled design. So what I typically do when I design something, I design all the parts first. And that way I can just copy and paste them into the actual design and be just quick at producing the design. So that's what I'm gonna do. I have to do this little pump. I'm gonna do it, and you don't have to, I mean, you can, for the most part, you don't have to get everything absolutely perfect. It's better that you get it dimensionally close as possible, but you can get a general shape and focus on hole alignment. Like if I'm a little off, like with the thread pitch, like I'm not going to worry about how much thread pitch I have here because it's not essential to what I'm doing. Because this thing has these connectors, these brass connectors that are going to go onto this heater pump, and that's really kind of the essential is how high up is that going to poke out and all that fun stuff. So that's kind of like what I'm going to be designing is the connection points and dimensionally accurate holes. I need to have the holes on there exact so that when I cut the metal, the holes will perfectly line up with that little pump, and I can mount it and not be drilling holes and doing a hack job. It needs to be computer precision, and it goes together just precisely. All right. So I'm gonna go ahead and take some measurements here. I got a 10 mil tube. Hold on. 10.03. Okay. By 50 millimeters long. .03. 50 millimeter. Okay. So I have a fixed nut, like this part does not twist or turn. 1, 2, 3, 4, 5 is a polygon. Dude, I was the worst shit ever in mathematics and geometry. But now that I do all this, I'm like, yeah, this is a tangent line that's parallel from this coincident relationship of these two parallels here. It's parallel to a coincidence of these two parallels. And I never remembered geometric or geometric figures. I still can't. I forget spheres and cylinders and all the basic shit is kind of what I remember. Hexagon, and polygon. I learned it because I constantly use it. It's like when it's not essential to you, you're not good at it. It's like now that I need mathematics and I need become the I'm still not good at it. Like you have brainy people who are like really good at manipulating equations, but you get really good at it when all you do is that. And when you're computer programming, you're constantly dealing with manipulating data and writing formulas and equations programmatically, but you're letting the computer do all the computations for you. 1.40. But we're going to go ahead and hold that out. I probably should wait on holding it out. Yeah, I'm going to wait on holding it out. Let's focus on the nut. Ooh, shit. I'm going to go down. 16.3. I'll throw a offset plane. There you go, 16.3 down. Do our polygon center and make it some kind of a .35. Let me check that out real quick. Oh, that's doing a radii. Oh, okay. Well, if that's the case, then all I have to do is divide by half. Yeah, hold on. So let's just say 17 divided in half, 18.5, 8.5, 8.5. Let me do a measurement from there to, actually from there to there. And voila. That should be dimensionally accurate. Let me check the two corner. 9.815. And 9.815. Alright, now how wide is that? 6mm drop. 6mm join. Okay. I need an origin here. Got my origin. So if you look at it, it's kind of got like the camera, maybe. So I get the camera to focus for you. So it's got those little like divots on the end there for the hose. I technically don't have to computer draft those, but it just kind of bugs me a little bit if I don't. It's 2.13. 2.13. Okay. Oh, I know how I'll do this. I'm doing it much the wrong way. Much to the wrong way. I have a better idea. 9.45 to 9.11. 9.45 to 9.11. 9.11 at the top. And 2.13. 2.45. Oops. .9 to 9.11. 10. Darn it, Cody. Why did I do that? So you can see why this a lot of jobs that pay to do this stuff. Pay is really good. Because this stuff takes a long time, 9.12. So now what we're going to do is we're going to do a loft cut from there to there. We're going to loft it, see how it's kind of very slightly angular. And then we're going to do negative 2.13 times 2 2.13. And we're going to do 9.11. 2, 2.13 times 2 times 2. Point 5. Okay, finish. We're going to do another loft cut. That's not going to work the way I wanted. Okay. All this, sometimes, oh, you can't see nothing. I'm blocking with my big ass head. I'm sorry, y'all. That was probably not too interesting. Let's be a pre-filled system. Will the consumer need to hook a water feeder tube up to it? If I were to sell them, let me dang, that whole time I was doing this whole stream was being being jacked by my software. Let's see here. Yeah, no, it would have to be sent empty. You don't want to put like water weight into a object that's going to go through a lot of oscillation during transportation. It's just begging for something to get broken. That's good. Alright, yeah, I was having a glitch out there where my cam software, I guess, was overriding everything. 2.13. Alright, boom. Okay, I have threads and a washer here. It's kind of just making this boring little piece. This thing's actually taking a little bit more time than it should. Only because it's being a pain in the rear. You know, I think I'm being a little too picky with the edge right here. Let me hide that. I'm going to do it the fast way. I'm just going to be fast with it. Especially when the things are not really all that important to be highly accurate, like this right here. It doesn't need to be that crazy accurate. I'm just going to do a conic curve from here to there. Kind of move this in a little bit. And then I'll do a revolve. Okay, real basic connector. Let's go ahead and thread it in. Not full length. I got maybe so just a little bit of thread there. About 8.3 millimeters of it. And how much clearance I got here? 2.73. I'll do 2.7. 8.3. Okay, modeled in. Alright. Down in, okay. So now I'm gonna just kind of speed this up. This is a bulkhead, so that we can connect our tubes to it. And let me drop down here. And I'm going to do a revolve. Oh. Okay, there we go. Alright, I'm gonna revolve that around. There. That looked no better. Kind of like a connection for the most bulkhead connections. Now let's round that off. Alright. Boom. Done. Alright, we got 2 washers to do real quick. And finally, a nut. Let me go ahead and hey, look how there's actually well, hold on. See that? There's 2 nuts in the screen. And when I remove this out of the camera, there's 1 left. Alright, let's do this washer. Enough fun. Enough fun there. 25.09. 25.09. We're going to do OD 25.9. 25.09. With the ID of 12.20. 12.20. Thickness of 1.5. Component. Oh, what the hell did I do there? There. Hold on. 1.5. New component. Okay. Let's kind of round that off a little bit. The washer really looks, and we got 2 washers here. We're going to call that washer. And there's 2 of them. So we're going to stack one on top of the other. This is what gives us our watertight seal. I'll probably throw silicone on there just because. So if you see the threads here, in between the two washers is where the metal has to go for the bulkhead going into the water reservoir that that we're going to be pumping water into, and water should be getting pressed out of. So we are going to have pressure. We're going to be basically, but that's going to act like a resistance. The question of this entire design is, this little pump have enough power to overcome that pressure? I could go through this entire design and fail. So before I do that, before I actually pay the money to go cut the metal for this, I'm going to hook this little 12-volt pump up, because it's a 12-volt pump. It draws about 1 amp. I'm going to hook some tubes to it, and I want to see it move some stuff. Like, I want to, you know, let's see if I can make it fill up a balloon. Like, if I can make it fill up or I'll go buy me a 3-liter jug when I test this pump. I got an idea. I'm going to buy like a 3-liter jug, 2 of them, hot glue the shit out of one. Like, I'm going to put tube into one, connect it to another, and I'm going to make it pump water into it, and I want to see water backflow from one of the 3 liters into another. That way I can kind of get a sense of how it deals with pressure. Otherwise, that pump, if it doesn't have enough pressure to overcome, or enough you know, pumping power to overcome the volume displacement that's inside that heater tank, well, the whole problem will, you know, the whole thing will fail. All right, let's see here. This little nut here. Draft that guy in, and then we'll call this part done. 15. So we'll just say 7.5. 7.5 with a 10 mil. What should I call it there? And 4 components, 4mm high, hot nut, okay, let me hide this. Gotta throw thread into it. Bring it back. Alright. So this thing is now, let's go ahead and put this together. I gotta slam down some water. I feel a little like a little dehydrated, or I need to eat more. So I'm gonna put the 2 washers on. There. Alright, that one's done. Let me save this project as hot bulk, or I'll just call it bulk. Alright, close that out. And now I'm going to design this little switch right here. So this one will be fairly quick. So I'm not going to be as really the only thing I have to get dimensionally accurate. Let me bring this back up. Is there's the way this switch gets mounted is you got to unscrew this nut right here, and so you make a hole as big is this round part right here, and then the nut goes over it, and that's what kind of like, it's kind of like a bulkhead. That's what clamps it down. So let me go ahead and get to drafting this. I'm gonna do the box first. We'll do, so what's it, 29 by 15.24. 29 by 15.24. And 6.84. $14.74. 23.48. Let me move myself out of the way so I'm doing what I did earlier. 23.47. 15. 7. 15. And that is going to be 9.08. Okay, and then we got two little prongs right here. Little bottom of the terminals we're going to solder onto. Okay, those are 6.35 wide, 0.76 thin. 7.35, and they are 9.77. Okay. Actually, let me go back to that. This is 8.5. 5. Hole 3.31 diameter. .54. 1.54 plus 3.41 divided by 2. No. Oh, no wonder. I was, what the hell? And that still is not right. That's why. We're gonna 11.7 by about 12. Okay. Let's do, we got an idea. Include 3D geometry. Gonna dimension that. Let's say the toggle switch is 20 millimeter long. 20. Okay, let's move that up. Whoa there. Let me do this a different way. That's my problem. You know, it's not tilted that much. Let's boom. All right. And choose about 5.87, 5.87. Let me cancel that there, finish that, go here, it narrows down to about 4.5, finish, we're gonna loft that to there, join, okay. And I've got a Oh, I got a nut I gotta do. Let's see. 4.8. 4.8. 14.8. Say 15. Let's do some 5. 1. Let's call that 12. New component. It is about 2 mil wide or 2 mil high. And then we have a little lock, like a little lock nut. Do 12. We're gonna do 12. We'll do 14. And we're gonna break it. We're gonna do a point break right here, right there. Hide that nut. What the hell was that? Hide the nut. It's not letting me do that. It's not letting me do it. You will comply. 14. Let me. There. There. Ha ha ha. All right. I'll do 2 by 5. And then we'll sweep, darn it, well, sweep that along this line here. Yeah, I guess it's okay. I'm not sure. Alright. Now we get to paint it up. Make it look all pretty. Oh no, it's like chromed out. What am I doing? That's black. And then the top part is chrome. Stainless steel, let's see here. Okay. Whole object there and there. Let's take a look what that looks like. Render. Yeah. Alright. Good enough. I'm happy with that. You kind of edge that off a little bit. Make the little tiny changes right there. Like that. And she's good, my friend. Alright. Let me, 25, yep. Switch. Now I do the pump, and I'm gonna call it a day. I gotta get off here and start doing some Android computer programming. cramming Android. I got an application I'm gonna make specific. So I did a video. A lot of you watched the video I did on an application where the programmer actually reached out to me. So I'm actually like kind of excited that I got to deal with a person that understood my argument about his application. So there's an app called the Photon app or PPFD app that this Russian dude or what have you produced or developed. And I showed in a video how inaccurate his application is. And I understand his challenge of what he's trying to do. He was like trying to get the application to be calibrated under sunlight. Well, depending on if you got clouds, depending on where you live, depending on the phone model, from one sensor to another sensor, whenever these things come out of the factory, they don't fully calibrate these lux sensors that are built in, or these light sensors that are built in. And essentially all you're doing is you're converting a standard photo sensor, or a photoelectric sensor, or aka a lux sensor. You're converting it mathematically to PPFD. And you can get away with this a little bit, but the thing about a real PPFD meter is it actually has filters, and it has op amps for high sensitivity of small amounts of voltage change, while also being able to fully measure very high PPFD levels. So the problem with these cell phone PPFD apps is that after about like 800 to 1,000 PPFD, they get squirrely, and that's because the sensor just gets overloaded. It doesn't have a way to voltage divide the amount of it. Just once you get that much photons with how the electronics are designed, it would essentially need to have a voltage division circuit to be able to simulate a bit more of how high a PPFD sensor can go. A PPFD sensor can go to 3,000 plus PPFD, and each sensor does have a limited amount of range, and it comes down to a lot of the op amps and how you're converting up, stepping the sensitivity of that sensor. There's a lot of resolution issues in these sensors, and that's why you pay so much money for like an Apogee meter. And when I designed my own handheld PPFD meter, I dealt with a lot of different sensors before I just found one that I liked that could go high on PPFD level and measure accurately. And so when I see these people making these cell phone applications, and just converting, there's a very basic library for converting lux. And if you're even a novice programmer and have a little bit of object orientation and class inheritance or extended class inheritance knowledge, then this is kind of like 101. Like let's see, Java, Arduino, or Android, SDK light sensor example. Okay, if you go to the developer.android.com for the API overview on various sensors, then you have environmental sensors in the reference of the documentation for the particular call, and then the sensor is type light. That is the if I'm, let's see here, in C++, we'd probably call this a type space, or a namespace, or a templatized, probably a templatized class function for an environmental sensor parent class, or for, I guess, sensor, for sensor event. It's a sub of sensor event. So let's see here. No, this is not the example code I was looking at. Oh, here we go. So use the light, pressure, and temperature sensor. So essentially, right now with Java, I could copy this code right here. Android Studio. I'm gonna end up diving into another hour of fun here, because I actually have an Android phone hooked up to run the application on. But you copy this into your main activity, your Java main activity. You'll copy this guy into your Java main activity, and here's all your calls for your sensor event handling. You're going to process these. So what you don't have here in this code is a basic button. Like when I on button press, we're going to register an instance of the public class sensor activity. So this whole thing here is public class activity, and we're extending to activity class by implementing the sensor event listener class. And by taking advantage of both class member functions from this class member set, we have all these we have these public and private functions here, or these public and private types, data types. So this would be a basic instance and use of this object. This is object-oriented programming. So we would take this you could basically copy and paste this shit right into your application, and then it kind of gives you an explanation. See here, like, look at the red comments. Gets an instance of the sensor service and uses that to get an instance of a particular sensor. So in this case, they're registering type sensor. We were wanting to read the data of type _ light. So that's the kind of sensor that we would be creating an instance of to start handling. And then on accuracy changed, what's really cool is, if the sensor accuracy changes, you can set resolution in here, and what you're probably looking for is you're checking for sensor event. On sensor changed, float millibars of pressure. In this case, we wouldn't be doing pressure, we'd be doing lux. We'd be just setting a variable, a float value, or we could truncate the float decimal value to just a straight integer value, truncating the decimal property so that we have a flat par value. And then to control how much or how fast the thing is reading, we could throw a little bit of delay in the event handling of getting the data from the sensor. So I'm going to be writing an app to read Lux, but to fix the problem that a lot of these PPFD apps have, that they've been basically, the problem they've been facing is they don't have a known controlled source to calibrate against the data set from the sensor. And the sensors in your phones are very limited. How do I get a sensor from this old A10 that maybe the light sensor that's manufactured into it is less sensitive than the light sensor in your Samsung Galaxy S20 or 21? When you take a lux reading with either one, depending on the manufacturer at the time when they get that sensor, its sensitivity to changes of light is going to be different. You're going to have radical differences, and that's why in the videos where I not only have videos, I think School of Crops also tested this out. I've had multiple people test a real PPFD meter against the PPFD apps that they put out there, and they're very inaccurate. But at the same time, sometimes they're spot on. So how would you know? There's only one way to know, and I'm aiming to solve that problem by building a NukeHeads PPFD app, where on the app you're going to have a calibrate button, very simple calibration button. You're going to put your phone 1 foot underneath like our gamma ray or gigawatt. So on the app you'll have a little checkbox or radials. Like if you have a gamma ray, you'll checkbox gamma ray. If you have a half gigawatt or a gigawatt, you'll checkbox whichever grow light you have as the calibration source. And what I'm going to be doing is I'm going to take two different actual very expensive quantum flux density meters and a spectroradiometer, and at 1 foot down underneath a gigawatt, underneath a gamma ray, and underneath a half gigawatt, I'm going to measure the PPFD level under all three lights. So this way I have a known produced golden value of calibration to reference the reading from a phone that may have a different light sensor. So for that, it doesn't matter from phone to phone to phone what sensor you have, as long as you have a Nukeheads grow light, this application will basically put you spot on accurate. And once you calibrate under one of my grow lights using the app that I'm going to design, then you can measure any grow light because it's actually calibrated to a known source. Versus going outside and putting under sunlight, hitting calibration, and praying that, you know, it's going to be semi-accurate. And that's all these PPFD apps are doing. They're making you go outside, take a PPFD reading, and when you're in the bright of day, the PPFD you're getting from the sun is going to be way higher than, you know, going out early morning or afternoon. So how do we solve that problem? We use a controlled known light source with a known data set, and then we compare that data set to the reading from the sensor. So now after you've calibrated that application to the grow light, at that very point, I'm going to be comparing what the Lux sensor is reading from, you know, what it's reading under that gamma ray, and it's going to compare what it's reading versus what the actual controlled known PAR level at 1 foot down under a gamma ray should be. Then it will ratio that difference of value and then multiply that quotient into a product of a PPFD offset and have an accurate representation of a real PPFD reading. Now the problem and challenge for me is I have an ideal of virtualizing this phone, the limitations of the electronics on the phone, to make it be able to read much higher than what everyone knows, every programmer that does basic PPFD reading with this class right here that I'm showing you, this class code. This is all that you're looking at when you look at PPFD apps. They're running this right here. This, whatever lines of code right here, is all that they're using. You build a Java button, you run this code, it takes a reading, it's highly inaccurate, it may be accurate, it's hit and miss. I'm going to solve that problem with the experience I have designing actual handheld PPFD meters and understanding the code logic behind it. The only thing I have to bridge and gap is, as a C++ programmer, Java programming language is very similar in syntax and it's very familiar. And so I'm now going to friggin' make a phone app just because, well, I have a reason to now. You know, it's like you learn complicated and hard shit and it becomes easy if you have a purpose. If you don't have a purpose, it's like, oh, that's so hard, that's boring. Anyhow, let me get back to designing here. We're going to make this little this hot water pump. So there's a little heads up on what I'm going to be doing after I get off this live stream. Okay. Man, I really hope this pump's got some pumping power. It feels like a beefy little bastard. I think it's going to be pretty potent. I mean, it's got a tiny little ass, what do you call it? Not a fan, but damn, I am feeling it. I need to like impeller. There we go. I need to probably go eat. Been working and need to chug down water. Pop out these little plastic things. I want to do the base first, and then we'll do the rest of the design. I need to pop out these little plastic parts so I can get a more definitive hole size, so I can fit the proper screw in there without breaking it and have everything mounting down the right way. I think after I do this water-cooled grow light, then we're going to do the DaVinci grow light. So the reason I'm just jumping right back into programming and brushing the rust off and getting my mind back into thinking code. Because the DaVinci grow light is going to tap into everything I know. It's going to use every freaking thing that I know. But at the same time, it's going to be, now that I've accomplished a lot with the chassis designs I've done recently, the chassis isn't going to be the hard part. None of it's going to really be hard. It's just going to be a lot of 3D modeling and design work. Like putting CO2 sensors. If I can find a laser distant or a laser temperature sensor that can read 5-6 feet away, then we'll be able to do vapor pressure deficit by reading the canopy stomatal inductance or the temperature of the leaf, of the fan leaves. Take that temperature, and with an equation of relative humidity, we'll be able to quantify a vapor pressure deficit. And I'll put into a GUI application. I'm going to be writing a Visual C++ GUI application using Arduino libraries and Visual Studio's native GUI framework. 45.10 to create a application on the touchscreen that I'm going to design into a grow light. So we're going to have a Windows 11 operating system in a grow light. I've talked about this for 3 years, but now I've got the warehouse space, machinery, and higher technical capability to do it all. You know, yeah, you don't just wake up and know all this shit. You gotta like spend a lot of time learning. When I vanish off of YouTube and no one knows where I'm at, they're like, "Where's Cody at? He's not posting on Facebook. It's been like a week." It's because I have to like get away from everything and just like I went and bought $300 of Barnes and Noble books, and most of the time when I buy books, I'll buy like all these books, right? And then I tend to read them, and then they hit the shelf. So, you know, I went through another habit of trying to at least scan through and sectionalize each useful each useful chapter of a book. And all my books are technical, like they're not like nonfiction or whatever. 45.11. They all teach you something. 45.11 by 32. Okay. Let me see here. I think I'll go about it like that. 5.34. 5.34. Darn it, what am I doing there? Yeah, I'll just go ahead and do that and that. Dimensional. Or dimension it. 4. Okay. 6.53. Looking good. .78. Oh, I got something checked up there. 5.4. That's why. Let me come back over here. Are any... Oh. Okay, stream's still going. Sometimes my stream stops. 3.74. Okay. Point five. All right. Okay, that's good. Boom. Okay. All right. What we got here? 3. Okay. $36.75. Hmm. Two sides. 40.11. .5. Okay. Let's see here. 9.23, 9.23. tubing. Okay.
Unknown caller.
for today. Oh yeah, well, whoever watches it, thank you for watching. It's kind of a slow, boring thing to watch someone design parts, but some people may find it interesting out there. It's a time-taking task, that's for sure. I'm gonna go ahead and kill the live stream. Y'all have a good